So this is the presentation, and so I'm going to go through this slideshow in a little bit of a different way than I intended, but let's go through it anyway. So this lecture is an introduction to quantum error correction, and to justify why we're doing this, first I should talk about why we need to do quantum error correction. And it's because, say, if you use the devices that we have available, so you can go to quantum-computing.ibm.com and of course run jobs on real devices. And if you do that, then you'll find that if you set a qubit to be 0 and then you measure it, then it's mostly but not always 0. And if you set it to be 1 and you measure it, then it's mostly but not always 1. So you find that these devices don't actually work exactly the way they should. Each gate that you do is slightly wrong, and the qubits will get perturbed by external forces as an interaction with the environment is what we call this. And the measurements that we make sometimes lie. Sometimes it's a 0 and you measure it and it tells you it's a 1. Now this isn't something that's uniquely true for superconducting qubits, but the same is also true for all other ways that you might imagine to make a qubit out of some physical system. So there's other ways of making qubits, such as spin qubits, topological qubits, photonic qubits, and all other kinds of things. This is just sort of random words for you at the moment, probably. But there are many ways that people have tried to make this thing that you've been learning about for the past few days, to make it in real life. And they use different physical systems to do that. And anything that they use, it's always going to be a little bit rubbish. And there's no way of getting around that. We can make it as good as we can, and we can reduce these effects as much as we can, but they will always be there to some degree. And when you're thinking about running an algorithm like Shor's algorithm on very large numbers, the number of gates that you need and the circuit depth that you need to run that is so great that even if you reduce the errors to them being effectively happening one in a million times, then if you've got a million things going on, then one of them is going to happen, and that is going to mess up your algorithm. So there is no way to reduce the noise low enough to get away from the fact that they are always going to be a little bit imperfect. So yeah, if we think about the algorithms that you've looked at so far, so if you think about the standard, what I would call textbook algorithms, like Shor's algorithm, Grover's algorithm, for factoring and search respectively, these assume that qubits are perfect. When people are studying quantum computing at this sort of computer science level, where they're thinking, what can one do with qubits? How can one make algorithms out of them? And it's always done with the idea that these qubits are absolutely perfect. They are exactly the two-dimensional quantum systems that you will have learned about in the last few lectures. But if you run these algorithms with the actual physical qubits, so qubits that are physically there on a device made out of a physical system, then you'll get not so great results because the algorithms have been designed assuming that they are perfect, and they are not quite perfect. So this is a graph from the section of Grover's algorithm in the textbook, where it is searching for these two particular bit strings, and it's run on a real device, and you find that it does indeed, with highest probability, find these two particular bit strings. And there's a car going outside at the moment, so maybe there's a bit of background noise. But with mostly it does find these, but there is also some probability it says, oh, hey, this is the correct answer some of the time, where it's not. This is not a correct answer at all. And that's entirely because of the effect of imperfections in the gates increasing over the course of the algorithm. And this is just on a 3-qubit variant of Grover's algorithm. If you scale this up to much larger systems, then the effect of the noise is going to, at some point, overwhelm the fact that you can, at least in this case, see what the right answer should be. So this causes us a problem The problem is, if we want to run algorithms, we need flawless incarnations of the idea of quantum information. These perfect things that really are described by the exact mathematics that you've been learning over the past few days. But what we have is a noisy version of that. So we need this flawless incarnation of the idea of quantum information, a perfect qubit. We call these logical qubits, but what we have are physical qubits. So what do we do in this regard? Well, either we can just try and use physical qubits as if they were logical qubits, and if it doesn't work, then oh well, but we can say what works. And for that, we'll find that not much really works, unfortunately. Or we can try to use the physical qubits to somehow build a logical qubit. So in some ways, to make something that is more than the sum of its parts, to take many noisy qubits and somehow out of that make a noiseless qubit. And that is the idea behind quantum error correction. So yes, quantum error correction is how we do this. Now, typically, we need many physical qubits per logical qubit. We can't just take a physical qubit and wave some sort of magic wand and all of its imperfections disappear. It becomes the logical qubit that we need in our algorithms. Instead, we typically take many physical qubits per logical qubit. And this is an example here. This is a grid of 17 qubits, 9 of them in black and 8 of them in this sort of outline circle. You don't have to understand what this is at the moment, but this is a representation of the smallest version of a very popular error correction code, which provides a little bit of protection. So to get a logical qubit, which isn't perfect, but is a little bit better than the physical qubits that it's made out of, you need 17 physical qubits to make that slightly better logical qubit. And if you want to make an even better logical qubit, then you have to use even more qubits, physical qubits. If you want to make something which is effectively perfect, then you might need thousands, at least, physical qubits per logical qubit. So the overheads in quantum error correction can be pretty horrible. And this is why we don't use error correction in our current devices. We don't have the overheads. If we used error correction, we might, with our biggest device, be able to give you one logical qubit out at the end. And that's probably going to be underwhelming for most people. So for the long-term goal, to make something that can run Grover's algorithm, Shor's algorithm, and everything, we are working towards being able to do quantum error correction. That is something that we are building up on over time. At the moment, we're doing proof of principle experiments on error correction, but we are getting better and better to show better and better logical qubits. But in terms of actual applications in the near term, we imagine more that we will try and make do and mitigate. So we will not try and use logical qubits, but we'll use the physical qubits that we have and just try and mitigate errors by less formal techniques than we do for quantum error correction. So this is an overview of why we need quantum error correction. What we'll do in the rest of this lecture is look in detail at the ideas behind error correction, both classical, although we won't go into the real depths of classical error correction theory, and we'll also, of course, we'll look at quantum error correction. For this, we will go through 2 specific examples of ways how to do quantum error correction. One is the repetition code, and the reason why I want to tell you about the repetition code is because it's the simplest quantum error correction code. So I think it's the best example. But the bad thing about the repetition code, and the reason why that's not the only one I'm going to tell you about, is it doesn't actually do everything it needs to do in order to help us build proper logical qubits. And so for that, we're going to look then at the surface code, which fixes the issues in the repetition code. And the surface, there are many ways of doing quantum error correction, usually called something followed by the word code, but the surface code is I would say the most popular, the one that people think is most likely to be used in the end to do fault-tolerant error correction, or at least some variant thereof. In this, we will see in both of these codes all of the most important techniques which are relevant for all forms of quantum error correction, which are syndrome measurements, decoding, and logical operations. And these will mean nothing to you at the moment, but the idea of the lecture is at the end, they will mean something to you. So we'll begin by just looking into what is error correction as a whole, what is even the concept of error correction. And for that, we can think of a classical example. In fact, we can think of a very down-to-earth example of people talking to each other. So say you're talking on the phone, someone asks you a question, you need to answer that question with a bit of information. You need to answer that question in binary. So you could say 0 or 1 if you were a computer, but usually when humans talk in binary, they say yes or no. So you need to answer a question with yes or no. Maybe you're being asked, do you want pineapple on your pizza? Yes or no? And there's two important things now to consider. How likely it is that you will be misheard. So maybe it's a perfect line. There's no flaws in the line at all. You know that everything you say will be heard in absolute detail. So in that case, if you don't want pineapple on your pizza, you can just say no, and you'll know that they have understood that. But maybe it's a noisy line, and if you say no, they're not really going to hear. They might think, "What was that a yes? I'll put pineapple on." So what is the probability that you're going to be misunderstood? And also, how much do you care about being misunderstood? Because there's no way that everything can be perfect. This is just a fact of life. So there is always some probability that you're going to be misunderstood. Like one in a trillion billion chance that aliens are going to intercept your message and just flip it to be annoying. So there's always going to be some probability something's going to go wrong, and you can think, how much do you care? So maybe you don't really care whether you have pineapple or not. This is not an issue that affects you. You know that some people get very passionate, but you particularly don't care. So then this would be quite low, but if you have very strong opinions on this issue, then this would be very high. And then once you have these numbers, you can think, well, if the probability of getting misunderstood is very much less than the acceptable probability, so it's much less likely to be misunderstood than the limit that you care about, then you don't really need to worry. You'll just say yes or no, whatever. But if you really want to get your message across, then you will have to do something rather than just saying yes or no in order to ensure that your message really is understood, despite the fact that the line that you're using is too noisy. And what you would probably do without even thinking is repeat yourself. So if you really wanted pineapple on your pizza, you would say, yes, 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 yes. Are you kidding me? Yes, of course. And once a person has heard that, then even if there's some interruptions in that signal, it's pretty obvious you're saying yes. And if you say, no, 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 why are you even asking me that? Then it's pretty obvious that you're saying no. So adding in more information, repeating it many times, ensuring that there is some redundancy is a way of encoding our message. It's taking our message and expanding it to something bigger such that it becomes tolerant of small faults. And in this case, it doesn't matter if a few of those words that you're saying get discarded, if they just turn into noise, or if some AI misidentifies them and turns them into the other thing or something. It doesn't matter. Your message is still getting through just because the way you have encoded it in repeating it has made it more tolerant to small faults. So that is the encoding step. You are taking your information, a yes or a no, and you are encoding it somehow. And your yes becomes yes, 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 yes. Your no becomes no, 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 no. But at the end, the receiver has to decode the message. Now, in this case, it's fairly easy because your message is just many copies of exactly what you want to say. In error correction, sometimes the way we encode it is something more abstract. So if you receive an encoded message, it's like receiving an encrypted message. It makes no sense if you don't know how to unpack it. So it can be that sometimes we encode a message in that sort of form in order to make it more robust against noise. But in this case, it's kind of easy. What you could do is majority voting. So if the receiver received a number of yeses and nos, then if they receive more yeses than nos, then they'll probably think, well, that sounds like a yes. Let me get out the pineapple. In this case, a misunderstanding will only happen when the majority of the copies are flipped, which is possible, but it's unlikely. So if you say yes, instead of yes, you say yes, 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 and there's some probability of 1/10 that one of those words gets messed up, then the probability that one of those words gets messed up is on the order of 1/10. The probability that two of those words gets messed up is on the order of 1 in 100. So most of the time, your yes will be yes, yes, yes. On the order of 1/10 times, your yes will be, well, yes, yes, no, and also for yes, no, yes, and no, yes, yes. So sometimes that'll happen, but that's okay. People understand from the majority that you're saying yes. But about 1 in 100 times, you'll get something like two of those yeses perhaps being flipped to a no, which is quite a weird error model, to be honest. When you're talking on a call, your words don't usually get turned into other words. But let's assume it for simplicity. About 1 in 100, there's a chance that even though you say yes, 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 because there's been two error events, it sounds like yes, no, no, and the person who is decoding this will think that you said no, even though you said yes. So that is a probability of something being incorrect. And the probability that that will happen is the probability that at least d/2 errors happen. So actually there's an error in this equation, but this is the probability that something goes wrong. I'm not sure if actually you can see me highlighting this because it's only capturing Chrome. But this is the probability. You can see it? Okay. So this is the probability that the person trying to decode your message decodes it incorrectly. And it's a sum over all of the possible ways that they can decode it incorrectly. So it should be the sum from d/2, which is half of d is the number of times you repeat. So d/2 is half the number of times you repeat, and then sum that to d. So it's all of the different ways that you can have half or more of the errors flip, and the probability of this scales, well, it's the probability that a flip happens to the power of the number of times you might get a flip, and there's binomial coefficients and all that. But really, it just scales with the kind of like the probability that a flip happens to the power of the minimum number of flips, which is problematic, which is half. So the probability of something going wrong, when you repeat 3 times, it scales as sort of p squared, because p is the probability that something is going to go wrong with each of your yeses or nos, and it's squared because you need to do it 2 times to flip the majority for 3. But if you repeated it 5 times, it'll be p to the 3. If you repeated it 101 times, it would be p to the 50. So the probability that the majority gets flipped decreases exponentially as you increase the number of repetitions. So as certain as you want to be that you do or do not get pineapple on your pizza, you can just make sure that happens by repeating yourself enough times. And I think this is something that intuitively we kind of know anyway. If we really don't want it, we would be saying no, 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 no. And I don't know why I picked this pizza example randomly, because I don't have strong opinions on pineapple on pizza. I know perhaps that's going to annoy some people, but there you go. Okay, so this is a simple example, and it in no way involved any quantum yet, but it has the very basics of quantum error correction or error correction, any kind of error correction, which are these steps of encoding and decoding. So we have some input, so some information that we want to protect. And then we put that through a process of encoding. We transform it in a way, usually by making it bigger, so it covers more information, more bits or more qubits, and we transform it in a way that makes it easier to protect. And then a process comes along which causes errors. So these are perturbations of the encoded message. So after that, we don't have exactly the encoded message that we started off with. It has been messed up a bit. And then we have the decoding process, which is basically solving a puzzle. We are given this messed up encoded information and we're told some errors happened, but we don't know where. Try and figure out the clues of where the errors might have happened to undo them and deduce the original message. So that is basically the puzzle at the heart of quantum error correction. In fact, I made it into a puzzle game a few years ago called Decodoku, which I think might even still be on the App Store, but it's not something that I really do much with anymore. But it might be fun as a game if you want to play something. Okay, so that is, well, this description is actually more geared towards error correction in telecommunication, where you want to send a message. So you encode it, errors happen along the way, you decode it, you get the message, done. This is not really the kind of error correction that is important for us, because we are doing computation. And in computation, we want to do error correction, which encodes our information at the beginning, and then we do a computation on that encoded information. We keep it encoded so that throughout our computation, any errors that happen, we can fix them. When we do operations in our computation, any errors that happen in those operations, any errors that we introduce just by the fact that we are doing an algorithm, we can fix them. And then at the end, we do decoding to get an output. Although actually it's not exactly that simple, because leaving everything to the end in terms of decoding is not a good idea. So what we'll really be thinking of doing is having our input, which is just our all zero state probably, then we encode it in some way, and then it keeps on going through a process of being, maybe we're doing an operation and that's causing noise, or maybe a qubit is just idle for a while and it's picking up noise from the environment. Whatever's happening, noise affects it, and then we need to fix that noise, so we decode and we re-encode, more noise happens, decode, re-encode, more noise happens, decode, re-encode, for as long as it needs for us to do our computation, and then we get an output. Although here I said we decode and then we re-encode, that is not actually fully true, because if we decode, then we get back down to an unencoded state, which is we have encoded exactly because we want to protect ourselves from the effects of errors. So once we decode, then we're back to being vulnerable again. We don't want to be in that state. So we want to do some decoding to fix things a bit, but without actually going back to our unencoded state. Now let's give you an example so that sounds less abstract. So let's just think of a single bit encoded using the repetition code. So what we could have here is that we have either a 0 or a 1. And if we had a 0, then we would, in the repetition code, repeat this 3 times to get 0, 0, 0. And if we had a 1, we would repeat it 3 times to get 1, 1, 1. And then let's say we go through some noisy process. We're not going to try and do an operation here. We're just going to consider the idea that the environment comes in and causes a bit to flip. And let's say that it's the last bit that flips, just as an example. So our 0, 0, 0 in that case would become 0, 0, 1 because the last bit has flipped. And if we had an encoded 1, our 1, 1, 1 would become 1, 1, 0. So then we can look at that, and we don't even need to decode that. We can look at that and think, well, there's 2 zeros and a 1. that 1 is out of place. Probably it should be a 0. And then we can identify that because it is not the same as the majority, that it's probably because of the majority voting in this code, the error. And similarly, if we found 110, we'd see similarly that this 1 is out of place. So we identify that as a problem, and then we can fix the error just by flipping that bit. So we can flip the last bit, and then whether we encoded a 0 or a 1, it fixes it. So we're going to do a process of trying to find, while it's still encoded, we're going to do a process of trying to find hints about what errors have happened so that we can keep on cleaning up our encoding while we're doing a computation. Okay, so this particular method with the repetition code would be fine for bits, but it's not so great for qubits. In fact, it's not even great for bits because it's kind of not a very... There are certain ways in which the repetition code, even for bits, is not a great code, but that's mostly due to overheads. We won't go into that, though, because that's all classical error correction, but we will go into why it's not great for qubits. So, for example, suppose we did not just want to have a qubit in state 0 or a qubit in state 1, but we wanted to have a qubit in a superposition state, some A0 plus B1. Then when we go through this process, what would happen? Okay, so instead of just a 0 or a 1 becoming 0, 0, 0 or 1, 1, 1, we would have A0 plus B1 becoming A 0, 0, 0 plus B 1, 1, 1. So I haven't said anything about what circuit we would use to do that, and you can think about what circuit you could use to do that yourselves if you want, but we would have some circuit which does that encoding, it does that transformation. Okay, then something happens. An error happens, and again, we take the example of a bit flip on the last qubit. Then we would get a superposition of A001 plus B110. Okay, then we go to the next step. We look at our qubits, we see what their values are to see if everything looks okay. So we measure them all, and that means that this superposition collapses to either being 001 or being 110. And then we look at that and we see, okay, this one's out of place, whichever it is. We fix it and we go round and around and around. But the trouble is, at that point of measuring, the collapse happened. We had a superposition, but as soon as we looked at our qubits, we ruined that superposition. So if we're actually doing a computation which requires that superposition, the fact that which we're not really seeing in this, because we've not got any operations in this particular example, we can't see that here, but in general, we might have some, we will be doing a computation. That computation would need the superposition to be there. The fact that we have destroyed it by inserting some measurements to check up on what's going on is a problem. From the quantum perspective, it is a problem. So to protect against one bad thing, which is our qubits flipping when we don't want them to, we actually caused another bad thing, which is the collapse of the superposition. Okay. Yeah, so I just thought I'd stop here and ask if there's any questions so far.
Yeah, we've got a few questions that I think are pretty relevant to what we're talking about right now. One, and you may get to this later, but since errors appear due to hardware, won't the error correction algorithms be different for different hardwares?
Well, that's a good question. Now, over the years, we, working on error correction, have been pretty much just as abstract in our thinking as people who work on algorithms. The only difference is that they assume that there's no errors and we assume that there is. And the errors that we assume are usually nice toy models of easy to understand algorithms. I always think of it as a little gremlin sitting next to every qubit, flipping or rolling a dice or something, deciding what to do. And if it comes up the wrong value, hitting the qubit with an X, a Y, or a Z. This is the sort of error model that we've traditionally looked at. And for that, well, at that level, it's the same whether you think of it in terms of spin qubits or superconducting qubits or whatever. Other than that, I think error correction will need to be tailored to the hardware to some degree, but also the way error correction works is it's kind of agnostic as to the errors, as long as the errors are local, so they act on single qubits or small groups of qubits, then the assumptions of error correction will work. But if you want the best performance, you will have to tailor it to the device to some degree.
Awesome. And then one more question for now. Aside from quantum error correction, are statistical methods used to normalize results, such as reducing columns in a histogram based on the distance to the largest column, or at least calculating the difference?
Yeah, so things like that would be called error mitigation techniques. And there is, if you look in the Qiskit textbook, there is also a section on some of the error mitigation techniques we have there, such as, like, you could imagine if you've got a single qubit, you could prepare it in the 0 state and then run many shots to see what the histogram looks like. And so it'll be lots of zeros and a few ones. And then you know, well, that's what a 0 looks like in terms of the histogram. And then you do the same thing for 1 to see what a 1 looks like. And then you do the same thing for anything arbitrary, and you can kind of look at the histogram you get from that and think, well, given that I know what a 0 histogram looks like, and given that I know what a 1 histogram looks like, what can I deduce about what this histogram should have looked like? So you can do, there's all kinds of error mitigation techniques that we know already, and I'm sure we'll develop more, because this is more relevant to the next decade than quantum error correction, arguably.
Awesome. I'll give it back to you to continue with your lecture.
Thank you. Okay, so we have a problem, and our problem is that we couldn't have identified this error without looking at our qubits and working out where the error was. But looking at our qubits destroyed our superposition. So how do we look at our qubits without looking at our qubits? How do we measure without measuring? Well, we just have to be careful about what we measure. There's no law against us measuring in some form. There's no law against us extracting information about the errors, but we just must not extract information that causes the superposition to collapse. If we ask a qubit, are you 0 or 1? It has no choice but to choose and collapse the superposition. But if we ask a group of qubits some other question, then it might not cause all of the qubits to collapse into particular superposition. So let's go into this in a little more detail. So yeah, we do need to measure, but we have to avoid learning about the encoded information. So let's look at an example where we have here a repetition code with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 repetitions. So if we encoded a 0, it would be this series of 11 zeros. If we encoded a 1, it would be this series of 11 ones. Now let's assume that errors happen on a particular set of qubits. So you can see the ones that are 1s affecting the 0, if that makes any sense. These ones that are flipped in the line that should be all 0s, the ones that are flipped to 1s, that's where the errors have happened. And if you look on the line that should be all 1s, I've made it so errors happen in exactly the same place there, so that we're having the same errors compared across whether they're encoded as a 0 or as a 1. And obviously, if we were to look at these values, we would see that those ones where the error has affected it are not the majority. So the majority voting would disagree with them and say that they're probably the ones that are the errors. But let's not do that. Let's instead go along and look at each pair of qubits along the line, or bit values, sorry, along the line, and ask, are they the same or different? Now, I think I asked this before, but I'll ask again. Can you see my pointer? Or can you only see when I highlight things?
We can see your mouse, and we can see when you highlight things.
Okay, the fact that you can see my mouse makes things a lot easier. So if you if you look at a pair of qubits, if you look at a pair of bit values, this is one that hasn't had an error, this is one that has had an error, and you'll see that they are different. So if you compare the values of these two things, then you'll find that they are different. So actually, I should say, if you compare the values when there has been no error, then these are the same, these are the same, these are the same, these are the same, 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 same. And similarly, even though they're a different value over here, still these are the same value as each other, these are the same as each other, and the same, and the same, and the same. So a signature of everything being good is that if you look at these pairs of values, you'll find that they always agree with each other. And of course they should. This is the repetition code. You're repeating things. They should agree with each other. And then if we see a single error in the middle of nowhere here, we find that this is different from both of its neighbors. And so the fact that it is different from both of its neighbors, well, seeing any of these two values being different is a signature that there is an error somewhere. And the fact that it's different from both of its neighbors is a fairly strong indication, although not conclusive, that this is probably the one that is in the wrong. Similarly, we can find that these are different, but these are the same, and these are the same, and these are different, and same, 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 different, different, same. So knowing that there's only two values, we can form these into two groups. We have this one, which is in one group, and then this one is in another group because it's a different value. Since these are the same as this value, that they're also in the second group. And since this one is different from that one, we know that we must have gone back to the first group. So these all belong to the first group. This is again in the second group. These are back to the first group. So even by just knowing whether these values are the same or different, without knowing what the values actually are, we can still do majority voting. We can still split it into two groups and find that one is in the majority, one is in the minority, and assume that the majority are the ones that haven't had the error and correct accordingly. So this and the exact same process would have worked exactly the same if we had encoded a 1, because it doesn't care whether we've encoded a 0 or a 1, because we are just looking at whether values are the same or different. We're not looking at what those values are. We're just looking at their relative values between each other. So the insight here is that we can still do majority voting without actually knowing what the bit values are. And we do that not by looking at the bit values, because that would of course have told us what the bit values are, but by instead only extracting the information about whether they're the same or different. So you bring your two bits together and you don't look at them and say, I don't want to know what you are. I just want to know, are you the same or different? And then they'd say, we're the same. And you say, oh, thank you. And then you go along querying all of these. And with that information, you would be able to do the error correction without knowing any of these values. And this would mean that even if you've got a superposition of lots of zeros and lots of ones, which became a superposition of this thing and that thing when you had errors, then when you ask a pair of qubits, are they the same or different, then the outcome does not disturb the superposition. It doesn't care about the fact that there's a superposition. It will tell you exactly the same results as if you had just done a 0 or a 1. So this is the information we need to extract. We need to do this thing where we're going to take two qubits and ask, in the 0-1 basis, are you the same or different? And extract that one bit of information, same or different, without actually looking at what they are. Okay, so how do we do that? I think this is probably the point where I would probably pick up my pen and start doing stuff in a written way, but because I'm doing it as a PDF on a browser, probably I'll have to stick with not doing that. But I think it should all be pretty much the same anyway. My handwriting is atrocious, and that's why I do things on PowerPoints mostly. So you're probably getting away lucky without having to look at that. Okay, so the way that we can do this with this task, which is to take a pair of qubits and see if they're the same or different without otherwise extracting any information, We can do this by taking an extra qubit. So for every pair that we want to ask this question, we take one extra qubit. So we have an example here where we have 3 repetitions. These are the colored values here. And then we have 2 extra qubits, which we usually call ancillas, which are the gray values here. So if we want to know whether these 2 are the same or different, then what we do is we use a couple of controlled NOT gates. So the first controlled NOT gate is controlled on one of the qubits we want to compare and targeted on the extra qubit, the ancilla. The other is controlled on the other qubit we want to compare when we're comparing this pair and targeted again on the same ancilla. And then what we do is we measure the ancilla and we get a result of either 0 or 1. So what is the relevance of that result? Well, let's consider the case where these are both 0, which is actually what we see here. In this case, well, a controlled NOT controlled on a 0 does nothing. So this does nothing. This one is also controlled on a 0, so it also does nothing. So our ancilla, which was initially 0, is still 0 at the end, and when we measure it, it tells us 0. So in the case where they are both 0, we get a 0 out here. Now, if they were both 1, if this was a 1 and that was a 1, then what would happen? Okay, so this is still initially 0. It goes along, it meets this controlled NOT. What does this controlled NOT do to it? Well, a controlled NOT, we can tell a story that it looks at the control and looks at whether it's a 0 or a 1. If it's 0, it does nothing, so that's exactly what we just talked about. If there is a 1 here, however, it will flip. It will do an X. It will flip this bit. It will flip this 0 into a 1. So in the case that we are comparing 2 1s over here, then this ancilla gets flipped from 0 to 1 after this first C0. But by the exact same effect, by the second C0, it gets flipped again back to 0. So in the case that these 2 are both 1, we have that we measure a 0 at the end. So whether they're both 0 or they're both 1, this measurement does not know, does not care. All it knows is if they are the same, it gives a 0. Now, what about when it gives a 1? So we see this example at the bottom here. So if they are different, so if this is a 0 as it is, and this is a 1, then this controlled NOT controlled on the 0 will do nothing. The controlled NOT controlled on the 1 will flip the ancilla. So the ancilla gets flipped exactly 1 time, flipping from 0 to 1. And so the answer you get out at the end is 1. And it doesn't matter if it was 0, 1 or 1, 0 that you're comparing. In either case, where they're different, you get a 1 at the end. So by introducing this extra qubit and by doing these controlled NOTs, we have found a way to not measure the qubits themselves, not get any information about what their value is, except that we are comparing whether they're the same or different. We want to know, well, you could be 0, you could be, so we take a pair and we say, well, you could be 0, 0, or you could be 1, 1, or you could be some superposition of that. We don't care. We just want to distinguish that from the case where you're 0, 1, or you're 1, 0, or you're some superposition of that. Can you distinguish those 2 cases of you being some sort of same or some sort of different? And by measuring the ancilla, that is exactly the information you get. 0 tells you that they're the same, 1 tells you that they're different. And by taking that information, we can get some information about what might have happened. So by seeing that these 2 are the same and these 2 are different, by combining that information, we can see, well, okay, that means that this qubit is the odd one out. So let's flip it to undo the errors that have happened. Okay, so we're not quite at the end of the repetition code, but we are at the top of the hour. So maybe it is a good time to take a break until, let's say, perhaps 1/4 whatever the hour is in your time zone. Although I think in India, you're off by half an hour. So 15 minutes from now is a way of being fine for everyone's time zone, I think.